Alright, so today we're looking at lesson 25, and we're going to look at radian measure along with angular speed and acceleration. Hopefully after this lesson you'll understand radian measure and angular speed and acceleration. In our work so far, we have always measured our angles in degrees. In Algebra 2 and in geometry you dealt with degrees. In pre-calculus and in calculus, hopefully you have dealt with some radian measures, and that's what we're going to be talking about a little bit. For many uses, it's going to be more convenient to measure angles in radians. So those of you that haven't heard of radians before, it's just another way to measure an angle. A radian is defined by the measure of a central angle of a circle, and it's going to be the ratio of the length of the arc intercepted by 2 radii to the radius of the circle. So if you draw a picture here, if these are both r and this length here of this arc is also r, this angle here is said to be 1 radian. So that's what a radian is by definition. Whenever we're going between degrees and radians, we're going to use these two unit multipliers, either pi radians over 180 degrees or 180 degrees over pi radians. Depends on which one you're starting with and trying to go to the other one. So we're going to convert 42 degrees to radians, and then we're going to convert 2.3 radians to degrees. So we're just going to use those formulas, or those ratios that we just had up on the board. So for 42 degrees, we're going to have to get rid of the degrees. So the degrees are going to need to be down in the in the denominator, so that they cancel. So we're going to have 180 degrees, and then on top, we're going to have pi radians. And so use your calculator, and you'll do 42 times pi divided by 180, and you'll get 0.73 radians. For this other one, you're going to do 2.30 radians, and so radians have to be in your denominator. They need to be down here so that they'll cancel. So pi radians, and then that means in your numerator you have to have 180. So 2.3 times 180, and then divided by pi. And we're going to go to 3 sig figs because that's how many we have in our original problem. So 132 degrees. So that's how you can convert between the two. It's not terribly difficult as long as you know your ratios. Now we're going to look at angular speed and acceleration. Angular speed of a rotating object is the measure of the rate of change of the central angle, which is theta, measured at the axis about which the object is rotating. So if you ever look at a wheel, a little wheel, or you could look at a gear, a little gear compared to a big one, if they are both traveling the same linear speed, this one is going to have to be turning a lot more quickly than this one. This one's going to be going a lot slower, because this one's going to have to travel more quickly to keep up with this one as it's rotating. So that's your angular speed. You're looking at how something is rotating. So your average angular velocity is defined by this formula, theta 2 minus theta 1 over t2 minus t1. And angular velocity is given by this symbol here. It kind of looks like a W. This is how I write it in real life. It's called omega. And so you may want to add that formula to your formula sheet. For instantaneous linear speed of a rotating object, it's going to depend on the angular speed and the distance from the point to the axis of rotation. So if I draw that big wheel, well, that's not going to be a very good circle. If I draw that big wheel that I had, and this is the center of it, here compared with out here. This one is going to have to be rotating more quickly than what's on the inside to be able to keep up with it. If you've ever been to a theme park, you may have been on rides where they go in circles, and if you're closer to the circle, you're going to get to go more slowly than if you're on the outside. If you've ever been to a playground where they had those little metal pieces, they're circles with a bar on them, and you have to get someone to spin you. You can't, I mean, you could run around it and then jump on it. You may have done that. But the closer you are to the middle, the slower you're going to be going, and then if you're on the outside, you're going to be spinning a lot more quickly. And that's what this is saying. The linear speed, the instantaneous linear speed, is going to depend on how far it is from the point of rotation, which is at the center. This is your formula that you're going to want to use. V is your linear velocity, R is your radius, and this omega is your angular velocity. If you have taken me for pre-calculus, this is the formula that the Saxon book uses for pre-calculus. V equals RL or LR. I don't even remember which now. But it's the same concept. So if you took me last year for math, then you should be familiar with that formula. Again, this is probably a good formula to add to your formula sheet. You can also add this one. This is your average angular acceleration. So it's going to be your omega 2 minus omega 1 over T2 minus T1. We're going to use the radian, and we're only going to use it when it's convenient, and when it's not convenient, we're going to just mark it out. It's a dimensionless unit, so it's the only unit that we are going to use that we can put it in if we want it, and if we don't need it, we just mark it out. So I'll show you how we're going to actually do that in a second. So we want to look at the instantaneous linear speed of this bug that's revolving on a record. So we're going to use our formula, V equals R omega. We want to know what is the linear speed, so that's the velocity. The radius is how far is it from the center. So it's 4 centimeters. And on these, you're going to want to put units because it's basically going to be a unit conversion problem. You're going to fill in your formula, and then you're going to have to convert units sometimes. And then our angular speed is 72.1 revolutions per minute. And we're looking for linear speed. So linear speed we can do in meters per second, or they gave us centimeters, so we can do in centimeters per second, or they gave us minutes, so we can actually do centimeters per minute. There's no reason to change centimeters and minutes unless they asked us to. So what we have to change is the revolution. I'm going to go back. We said the unit radian is dimensionless. We didn't say that revolutions were dimensionless. So on these, we have to convert revolutions to radians. So revolutions are going to go down here so that they're going to cancel. And the way that you can make it cancel, one revolution, one rotation about your circle is the same thing as 2 pi radians. And so if you multiply your numbers, you get 1,812.07, and your units are centimeters times radians over minute. And radians, we don't want it when we're talking about velocity, and that's where we can just mark it out. If you don't want it, then just mark it out, make it go away. So now we need to write our answer. And we have 3 sig figs, so 181, and then just a 0, centimeters per minute. And so that would be your answer for that one. We're going to do another one. This time it asks for the angular speed, and it wants it in radians per second. So we're going to start with our formula. V equals R omega, and it says the wheel is rolling along at 60 meters per minute. So if it's a unit that you could say that a car is running, like speeding along the road, or you are running, or an animal's rate of speed, that's going to be a linear velocity. That's going to be your V. So meters per minute, that's what we could say for velocity. So 60 meters per minute. And again, you want to always include your units on these because we're going to end up having to convert typically. Then the radius is going to be 2 meters. And we are looking for the angular speed, which is what we don't know. And so now we're going to have to divide by this 2 meters or multiply by 1 over 2 meters on both sides of the equation. And so this is going to make you be able to solve for your angular speed. So your angular speed is going to be 60 meters per minute, and then times the 1 over 2 meters. And now all we have to do now is get it into this radians per second. So if you notice, these meters are going to cancel out. And now we have it in minutes, and we need to convert it into seconds. So 1 minute is 60 seconds. And so the minutes will cancel. And so if you look, we've got it 60 and 60, and then a 2 in the denominator. And so if you multiply and divide, you'll actually end up with 1/2 or 0.5. And we only have per second. We don't have any other unit here. We need it in radians per second, and so radians is the unit that if we need it, we can add it in. So we need it in our numerator, so we can make it radians in our numerator and then divide by second. So radians per second. And we only had 1 sig fig in our problem, so 0.5 has 1 sig fig, so this would be your answer. Radians is the only unit that you can do like that. If you don't have it, you can just put it in. And if you have it and you don't need it, just mark it out. It's the only unit like that, okay? So that's how you deal with radian degrees conversion and then angular speed and acceleration. Your homework is 1 through 20, so make sure that y'all do those tonight along with the curveball questions so we can go over any questions you have tomorrow.